Okay, so we talked about the features of exponential functions yesterday. Today we are focusing on exponential regression, where you're given a table and we have to be able to use exponential regression like linear regression and quadratic regression to be able to find the equation. Remember, the equation is going to be written in this form, where y equals a times b raised to the x power, where a is your initial value, your starting point, which is also your y-intercept. B is your common ratio, which means what's my rate of change multiplier. So B will be that, and then X will be X. So if I jump right in, here's the calculator steps right here. I'm going to take a table and type it into stat. So I'm going to copy this table down correctly as it matched. Okay, so if I copy table down where my x values go on the left, -2, 1, 0, 1, 2, and my y values on the right. Exponential regression, which means you go to stat, over to calc, and exponential regression is actually not on the screen. You have to scroll down, which is 0 here. And then you just hit enter until you calculate. Okay, so again, A is referring to my y-intercept, B is referring to my multiplier. So how I can tell the difference between, well, let's just write it down. Let's round to the tenths place. So my y-intercept would be 3.7. My multiplier would be 3.3. And so if I wrote that equation, y equals my y-intercept times my multiplier raised to the x power, in that format. How I can distinguish between growth or decay is looking at this multiplier. If it is greater than 1, then it is growth. If it is between 0 and 1, then it is decay. So since it is greater than 1, this would be growth. I mean, you can tell based off the table itself, but it's good to know that as well. Again, another one, this one would be -2, -1, 0, 1, 2. This one would be 0.41, 0.286, 2, 1498. So if you go to stat calc, you can automatically just hit the 0 button instead of scrolling down to 0 and hitting enter. So it's just a quick way to do that. Again, if we round to the tenths place, the y-intercept would be 3.2. The rate of change would be 4.4. Since the rate of change is greater than 1, this is also growth, where my equation is my initial value times my multiplier raised to the x power. Let's do one more of those, where 0.0097, 0.078, 0.625, 5, and 40. Again, stat calc 0. This time, my initial value is 0.6, where my multiplier will round up to 8. And since the multiplier is greater than 1, this is growth, where y equals my initial value times my rate of change raised to the x power. All right, so then we're just going to focus on which one's which, just based off looking at an equation. So if I look at number 1, we're going to distinguish between whether it's growth or decay. And remember, we're looking at my common ratio, my b value here. If it's greater than 1, it is growth. If it is less than 1, then it is decay. Here on letter A, we're looking at what's in the parentheses. This is my rate. Since it is greater than 1, this would be growth. B, since it's 0.5 is less than 1, this would be decay. C, since this is greater than 1, this would be growth. D, since it's less than 1, then it would be decay. This one, it looks at first like it's less than 1, but it's in the parentheses is 1 plus, so that means it would be 1.025, which would distinguish that as growth. F would be 1 minus, which means 1 minus 0.4 would be 0.6, and that's less than 1, so that would be decay. Another way to tell that, if you have trouble with that, is to type it into y equals, each equation typed in just like you see it, where you raise to the x power. And you can just look at the graph and tell if it's growth or decay, if it's increasing or decreasing, just like that. Then you have some word problems references that you'll have to know. So number 2, since January 1980, the population of the city of Brownsville has grown according to the mathematical model where they have this exponential equation, where x is the number of years since January 1980. Explain what the numbers 720,500 and 1.022 represent in this model. So remember, the first value is our y-intercept, but if we're talking about in this situation, we're talking about the initial amount or the initial number of people in 1980, like that. The 1.022 is that rate of change. So that means it is growing at a rate of 1.022. So it is a growth. What would be the population be in 2000 if the growth continues at the same rate? So if we look at that equation where I have my y-intercept and that growth rate, how many years have passed from 1980 to 2000? That would be 20. So that x value would be 20 right there, which we can just type into the home screen to figure out what the population will be if this rate continues. And it's a huge value because we're talking about population growth. So we're talking about 1,113,402 because we're talking about people. We want to round to the whole number. Use this model to predict what the when the population will reach 1 million people. Well, we already figured out that it's already more than a million at 20. But to figure out how much it'll be at 1 million, we put the y equals is that total to that equation where we leave x as x, like that. And we can just do y1, y2, or solve for that, but it would be a little tricky. So we just do y1, y2, where 1 million goes into the first line and 720,500 parenthesis 1.022 raised to the x power goes into the second line. Of course, we're talking about millions of people, so I'm going to have to zoom out a ton, where you can change the window as well. So let me do that. Since my y value is super huge, we're going to change that to 1,000,001. Just kind of playing with it. There it is. And there's that exponential growth. Looks like a linear function. Oops, still can't see it. Now you can see the exponential growth. All right, there's where it crosses. So we want to find that intersection. So you do second trace 5, enter, enter, enter. And how many years would it take to reach exactly 1 million? Would be about 15 years. Where x is your time. A population of 800 beetles is growing each month at a rate of 5%. Write an equation to express the number of beetles at this time. So where 800 is my original amount, since we know that it is growing, 5% written as a decimal is 0.05. Well, we have to remember that growth itself has to be greater than 1. So we learned this exponential growth formula at the beginning of the year, where we have a parentheses 1 plus the r raised to the t power. So we're technically doing that. It's just condensed. So in order for this to work, it would be 1 plus 0.05 raised to the t power. Or x, technically. So there's the equation. How many beetles will there be in 8 months? Since we're talking about, each month. So we have to figure out, using that equation, we're going to put 8 for t. And the only reason we can put that for t, it is referring to months. So 1 plus 0.05 raised to the 8th power. So after 8 months, the beetle population will be 1,182 because you can't have a decimal of a beetle. So there it is. So that's just taking some real world examples and using the formula.